There is a moment in every space mission launch when the rocket clears the tower and the commentator says something like, "Beginning its journey to Mars," or "On its way to Jupiter." And the phrase makes it sound like the spacecraft is doing something straightforward, like driving to another city, like the destination is fixed and the path is direct, and all that remains is to cover the distance. None of that is true. The planets are not fixed. They are moving, all of them, continuously, at speeds ranging from 47 kilometers per second for Mercury to 5 kilometers per second for Neptune, each following its own elliptical orbit around the Sun, each at a different distance, each completing its orbit in a different period. The positions of the planets when a spacecraft arrives are completely different from their positions when the spacecraft launches. The destination you are aiming for is not where it appears to be. It is where it will be, months or years from now, when your spacecraft, following its own curved path through the solar system, finally intercepts it. The path is not direct. It cannot be. Pointing a rocket at Mars and firing straight toward it would fail dramatically. The rocket would arrive at the point in space where Mars was when you launched, and Mars would be somewhere else entirely, having moved millions of kilometers along its orbit in the intervening months. To reach a moving target with a vehicle that burns most of its fuel at launch and then coasts, you must aim not at the target, but at a point in space where the target will be. You must understand orbital mechanics. You must calculate trajectories that curve through space following the Sun's gravity, bending toward and away from the target, sometimes swinging past other planets to steal gravitational energy. And the transit times that result from this orbital geometry are not the times most people imagine. Tonight we are going to follow the actual journey times to every planet in the solar system. Not approximate times from a textbook, the real numbers. Why they are what they are, what varies them, what determines the fastest possible trajectory, what the missions that actually flew took, and what it would mean for any human being to experience those transit times not as a number, but as a lived reality. Because the time it takes to travel to the planets is not just an engineering fact. It is a statement about the scale of the solar system, about what it means to leave the world you know and travel through empty space for months or years toward a destination you cannot see, getting larger, in an environment that will try to kill you in multiple ways simultaneously, with communication delays that grow from minutes to hours as you move outward. The numbers are astonishing, and following them honestly produces something that no map of the solar system can quite capture: the actual sense of how large this system is, how isolated each destination is, how profoundly travel between planets differs from any other kind of travel human beings have ever undertaken. Let us start with the fundamental physics that determines everything else. The planets do not sit still. Understanding how to reach them requires understanding how they move, and specifically understanding a counterintuitive fact about how things move in orbit that determines every trajectory in the solar system. In orbit, everything is balanced. An object orbiting the Sun is in a continuous free fall, falling toward the Sun under its gravity, while simultaneously moving sideways fast enough that it keeps missing. The speed required to maintain this balance depends on how close you are to the Sun. Objects closer to the Sun orbit faster. Objects farther away orbit slower. This is Kepler's third law, derived from Newton's gravity, and it governs everything. Earth orbits the Sun at approximately 29.8 kilometers per second. Mars, farther from the Sun, orbits at approximately 24 kilometers per second. Venus closer at approximately 35 kilometers per second. Mercury closest at approximately 47 kilometers per second. Neptune farthest at approximately 5.4 kilometers per second. Now imagine you want to go from Earth to Mars. You might think the way to go faster is to fire your rocket toward Mars, but this is wrong. Firing your rocket toward Mars would change your orbit in a way that moves you sideways, not directly toward Mars. The geometry of orbital mechanics means that to change your distance from the Sun, to move from one orbit to another, you must fire your rocket in the direction you are already moving, or against it. If you fire your rocket in the direction of Earth's motion, adding speed, you raise your orbit. The path curves outward, away from the Sun, toward the outer planets. If you fire against your motion, slowing down, you lower your orbit toward the inner planets. The most fuel-efficient path from one planet to another is called a Hohmann transfer orbit. Named after Walter Hohmann, a German engineer who calculated it in 1925 before space travel was possible, the Hohmann transfer is an elliptical orbit that connects the two planets' orbits. At one end of the ellipse, the perihelion, the spacecraft is at the inner planet's orbit. At the other end, the aphelion, it is at the outer planet's orbit. To execute a Hohmann transfer from Earth to Mars, you fire your rocket at Earth's orbit to speed up, entering the transfer ellipse. You then coast, engines off, for approximately half the ellipse, following the curved path through space while the Sun's gravity gradually slows you as you move away from it. When you reach the other end of the ellipse, you are at Mars's orbit. If the timing is right, if Mars is at that point in its orbit when you arrive, you fire your rocket again to match Mars's orbital velocity and enter orbit around Mars. The Hohmann transfer uses the least fuel of any trajectory between two planets, but it also takes the longest time of any feasible trajectory, and it can only be executed during specific launch windows, periods when Earth and Mars are in the right relative positions so that Mars will be at the end of the transfer ellipse when the spacecraft arrives. These windows occur approximately every 26 months for Mars, the synodic period, the time for Mars and Earth to return to the same relative configuration. Miss a window and you wait 26 months for the next one. This constraint, the combination of orbital mechanics and launch windows, is the fundamental reality governing travel times in the solar system. You cannot go whenever you want. You cannot take a direct path. You must choose trajectories that work with the geometry of the solar system, and the geometry changes continuously as all the planets move. With that foundation established, let us go through each planet. Mercury first. Mercury is the closest planet to the Sun. It is not the closest planet to Earth at any given moment. That distinction alternates between Venus and Mars depending on orbital positions. But it orbits innermost at an average distance of 0.387 astronomical units from the Sun, compared to Earth's 1.0. You might expect Mercury to be easy to reach. It is close to the Sun. It is in the inner solar system. Surely a spacecraft heading inward would get there quickly. Mercury is, in fact, one of the hardest planets to reach, and one of the slowest to travel to. The reason is that counterintuitive orbital mechanics property. To go from Earth inward to Mercury, you need to slow down, remove energy from your orbit so that your path curves inward toward the Sun. But you cannot slow down enough simply by firing your rocket against your direction of travel. The fuel required would be astronomical, far more than any realistic rocket can carry. The solution which planetary mission designers use involves either extreme fuel expenditure or long, looping trajectories that use gravity assists from Venus to bleed off energy. And these trajectories take a long time. The Messenger spacecraft, NASA's Mercury orbiter launched in 2004, took 6.6 years to reach Mercury. 6.5 years to reach the closest planet to the Sun. It flew past Earth once, Venus twice, and Mercury 3 times in a complex choreography of gravity assists, each flyby using the planet's gravity to alter the spacecraft's trajectory and remove velocity, gradually lowering its orbit until it could be captured into Mercury orbit in 2011. The Bepi-Colombo mission, launched in 2018 by the European Space Agency and Japan's JAXA, is even slower. It will reach Mercury in late 2025, making the journey approximately 7 years. It requires 9 gravity assist flybys, 1 of Earth, 2 of Venus, and 6 of Mercury itself, to shed enough orbital energy to be captured by Mercury's weak gravity. Why so long? Why does reaching the closest planet take longer than reaching planets 3 or 4 times farther away? Because of the orbital speed problem. Earth orbits at 29.8 kilometers per second. Mercury orbits at 47 kilometers per second. To orbit Mercury, your spacecraft must match Mercury's orbital speed. But to get there, you have fallen inward toward the Sun, where Mercury is, and as you fell inward, you sped up. Gravity accelerated you as you fell toward the Sun. Arriving at Mercury's orbit, you are moving too fast. You must slow down enormously to enter orbit. Every meter per second of velocity you must remove requires fuel, and the quantities involved are staggering. Gravity assists from Venus allow the spacecraft to shed velocity over multiple flybys without burning fuel, but each flyby takes time, and the resulting trajectory is enormously long. 6 to 7 years for a planet that is, when closest to Earth, only about 77 million kilometers away. For comparison, the distance to Mercury at closest approach is less than half the average distance to Mars. Yet missions to Mars take 6 to 9 months. Missions to Mercury take 6 to 7 years. The counterintuitive nature of orbital mechanics means that close does not mean fast, and the most fuel-efficient paths are rarely the most time-efficient. If you had unlimited fuel, enough to simply accelerate toward Mercury on a direct trajectory and then decelerate to match its orbit, you could reach Mercury in approximately 3 to 4 months. But no existing rocket is remotely capable of carrying the fuel required for this. The practical answer to how long it takes to fly to Mercury is 6 to 7 years with current technology. Let us move to Venus. Venus orbits the Sun at 0.723 astronomical units, closer than Earth, but not as close as Mercury. It has a synodic period of approximately 19 months, the time between successive launch windows from Earth. At closest approach, Venus is approximately 38 million kilometers from Earth. At farthest, approximately 261 million kilometers. Getting to Venus is significantly easier than getting to Mercury, though it still requires understanding orbital mechanics rather than intuition. To reach Venus, you need to lose orbital energy. Slow down to drop your orbit inward. But you need to lose much less energy than for Mercury, because Venus orbits only moderately faster than Earth, at approximately 35 kilometers per second. The Mariner 2 spacecraft, the first successful interplanetary mission in history, launched by NASA in August 1962, reached Venus in December 1962 after a journey of approximately 3.5 months. It became the first spacecraft to successfully conduct a flyby of another planet, returning data about Venus's atmosphere and surface temperature. The Soviet Venera series of missions throughout the 1970s and 1980s took similar times, typically 3.5 to 5 months, to reach Venus. The Messenger spacecraft used Venus for gravity assists on its way to Mercury, demonstrating that Venus is a conveniently placed gravitational tool in the inner solar system. The faster end of Venus transit times is driven by favourable launch windows and direct trajectories, around 3 to 4 months. Slower trajectories, extending to 5 or 6 months, involve less optimal launch windows or more complex paths. For human missions to Venus, which have been proposed theoretically though never funded, the transit time would be similar. But the thermal and radiation environment at Venus orbit, much closer to the Sun than Earth, would be significantly more extreme than for Mars missions. Now Mars, the planet most discussed in terms of human exploration, and the one whose travel time has been most publicly debated. Mars orbits at 1.524 astronomical units from the Sun. Its orbit is more elliptical than Earth's, meaning the distance between Earth and Mars varies considerably more than the distance to Venus. At the most favourable oppositions, when Mars is at perihelion and Earth at aphelion, Mars can be as close as 54.6 million kilometres. At unfavourable oppositions, it can be nearly 100 million kilometres away. At its most distant, on the far side of the Sun from Earth, it is over 400 million kilometres away. This variability directly affects transit times and the energy required for missions. Missions launched during favourable oppositions, which occur roughly every 15 to 17 years for the most favourable configurations, reach Mars more quickly and with less fuel than missions launched during less favourable windows. The Mariner 4 spacecraft, the first successful Mars flyby, launched in November 1964, travelled for approximately 7.5 months before flying past Mars in July 1965. The Mars Pathfinder mission launched in December 1996 and landed in July 1997, approximately 7 months. Mars Odyssey launched in April 2001 and arrived in October 2001, approximately 6.5 months. Mars Reconnaissance Orbiter launched August 2005 and arrived March 2006, approximately 7 months. The Perseverance rover launched in July 2020 and landed February 2021, approximately 6.5 months. The pattern is consistent. Real Mars missions, launched during favourable or acceptable windows, take approximately 6 to 9 months. The Hohmann transfer minimum for a favourable launch window is approximately 6 months. Less favourable windows push this toward 8 to 9 months. What about faster trajectories? Faster Mars trajectories exist. You can launch during the window and use more fuel to take a shorter, more direct path that does not follow the minimum energy Hohmann ellipse. These trajectories trade fuel for time. The trade-off is severe. Cutting the transit time to 5 months instead of 7 months might require 2 to 3 times as much propellant for the same payload mass. Cutting to 4 months requires even more. These fuel penalties are significant enough that no Mars mission has used them. the cost of the additional propellant far outweighs the benefit of arriving a few months earlier for robotic missions. For human missions, the calculus changes somewhat. A human crew experiences every additional month in the radiation environment of interplanetary space as additional cancer risk and physiological deterioration. Cutting transit time saves cumulative radiation dose and reduces bone density loss and muscle atrophy. There are genuine health arguments for faster trajectories, even at the cost of substantially more propellant, if the propellant can be manufactured on Mars or derived from in-space resources rather than launched from Earth. SpaceX's Starship architecture assumes propellant production on Mars, which changes the mass budget significantly. With advanced propulsion, nuclear thermal propulsion, which could increase specific impulse by roughly a factor of 2 compared to chemical rockets, Mars transit times could be reduced to approximately 4 months. With more exotic nuclear, electric, or fusion propulsion, potentially to 2 to 3 months. But with currently flying technology, chemical rockets, the honest answer for how long it takes to fly to Mars is 6 to 9 months, depending on the launch window and trajectory chosen. And for a human crew, that means 6 to 9 months in the radiation environment of interplanetary space, in microgravity, in a spacecraft whose diameter is measured in meters, with communication delays to Earth growing from a few minutes near departure to 5 to 24 minutes near arrival, depending on orbital positions, with no possibility of rescue or resupply if something goes wrong. 6 to 9 months, one way. Then approximately 18 months on the surface, waiting for the return window to open. Then 6 to 9 months home. Total mission duration of approximately 2.5 years. Let us now move to the asteroid belt, which is not a planet but whose transit time illuminates the journey to Jupiter. The asteroid belt occupies the region between Mars at 1.5 astronomical units and Jupiter at 5.2 astronomical units, a broad ring of rocks and minor planets orbiting the Sun at distances ranging from about 2.2 to 3.2 astronomical units. The Dawn spacecraft, which orbited first the asteroid Vesta and then the dwarf planet Ceres, launched in September 2007 and reached Vesta in July 2011, approximately 3.75 years for a target roughly 2.5 astronomical units from the Sun. Now Jupiter. Jupiter is the giant, the largest planet in the solar system, 318 times Earth's mass, orbiting at 5.2 astronomical units from the Sun, with a period of approximately 11.9 years. At closest approach, Jupiter is approximately 588 million kilometers from Earth. At its most distant, approximately 968 million kilometers. The Pioneer 10 spacecraft, the first mission to successfully navigate the asteroid belt and reach Jupiter, launched in March 1972 and arrived at Jupiter in December 1973, after a journey of approximately 21 months. The Pioneer 11 spacecraft launched in April 1973 and reached Jupiter in December 1974, approximately 20 months. The Voyager 1 spacecraft launched in September 1977 and reached Jupiter in March 1979, approximately 18 months. The Voyager 2 spacecraft launched in August 1977 and reached Jupiter in July 1979, approximately 23 months. The Galileo spacecraft, the first Jupiter orbiter, launched in October 1989 and arrived at Jupiter in December 1995, approximately 6 years. But Galileo did not take a direct trajectory to Jupiter. It used a Venus-Earth-Earth gravity assist sequence, flying past Venus once and Earth twice, to pick up enough speed to reach Jupiter. The long journey was necessary because the spacecraft was too heavy to send on a direct trajectory with the available launch vehicle. The Juno spacecraft, currently in orbit around Jupiter, launched in August 2011 and arrived at Jupiter in July 2016, after approximately 5 years. Like Galileo, it used an Earth flyby for a gravity assist. The direct Hohmann transfer to Jupiter takes approximately 2.7 years. With more energetic trajectories, the kind Voyager used, this can be cut to approximately 18 months to 2 years. With gravity assists that add years to the journey, missions like Galileo and Juno took 5 to 6 years, but were able to use smaller launch vehicles. For any mission to Jupiter, the 588 million kilometre minimum distance, even at the speed of light, represents a communication delay of approximately 33 minutes one way. At maximum distance, 54 minutes. Any spacecraft at Jupiter is operating with a round-trip communication delay of over an hour. Commands sent from Earth take 33 to 54 minutes to arrive. Responses take another 33 to 54 minutes to return. Real-time operation is impossible. For a human crew at Jupiter, this communication delay would mean complete operational autonomy. Earth-based mission controllers would know what the crew did over an hour after the crew did it. The crew would receive advice and instructions over an hour after sending their question. They would be genuinely alone in ways that no human mission to Mars would be. The radiation environment at Jupiter is additionally extreme. Jupiter's powerful magnetic field traps energetic particles in radiation belts far more intense than Earth's Van Allen belts. The radiation dose rate in the most intense regions near Jupiter is lethal within hours for an unshielded human. Even the Juno spacecraft, hardened against radiation, has a limited operational lifetime at Jupiter before its electronics degrade. A human mission to Jupiter, assuming the transit time could be managed, would face radiation challenges that make the Mars mission look mild by comparison. Jupiter's moons, outside the worst of the radiation belts, are more feasible targets, but still demanding. Europa, the icy moon believed to harbour a subsurface ocean, is of extreme scientific interest. A crewed landing on Europa would require solving radiation shielding problems of a different order of magnitude than any previous mission. Let us move to Saturn. Saturn orbits at 9.5 astronomical units from the Sun, with an orbital period of approximately 29.5 years. At its closest, Saturn is approximately 1.2 billion kilometres from Earth. At its most distant, approximately 1.7 billion kilometres. The one-way light travel time to Saturn ranges from approximately 68 to 95 minutes. The Pioneer 11 spacecraft, after its Jupiter flyby, became the first mission to reach Saturn, arriving in September 1979 after a journey from Earth of approximately 6.5 years. The Voyager 1 spacecraft reached Saturn in November 1980, approximately 3 years after launch, but only because it used Jupiter's gravity to accelerate and redirect toward Saturn. The Voyager 2 spacecraft reached Saturn in August 1981, approximately 4 years after launch. The Cassini spacecraft, the most sophisticated Saturn mission ever flown, launched in October 1997 and arrived at Saturn in July 2004 after a journey of approximately 7 years. It used a Venus-Earth-Jupiter gravity assist sequence, flying past Venus twice, Earth once, and Jupiter once, to reach Saturn's distant orbit. Without gravity assists, a direct Hohmann transfer to Saturn would take approximately 6 years. With the gravity assist sequences used by real missions, the journey times have ranged from 3 years for Voyager 1, using an optimally timed Jupiter flyby during the rare planetary alignment that made the Voyager Grand Tour possible, to 7 years for Cassini. The communication delays to Saturn are striking. At minimum distance, a signal from Saturn takes approximately 68 minutes to reach Earth. At maximum, approximately 95 minutes. Round trip, over 2 to 3 hours. For any human crew at Saturn, Earth is not just far away in space, it is far away in time. A question asked of mission control would receive an answer a minimum of 2 hours 16 minutes later, more typically 3 hours or more. The crew would not merely be isolated, they would be operating in a different temporal reference frame from their support network, unable to receive assistance on any timescale shorter than hours. Saturn's moons present extraordinary destinations. Titan, with its thick nitrogen atmosphere and liquid methane lakes. Enceladus, with its active water vapor geysers erupting from a subsurface ocean. These moons have been observed by Cassini in extraordinary detail. Titan was landed on by the Huygens probe in 2005. Dropped by Cassini, it descended through Titan's atmosphere and landed on the surface, surviving for about an hour and sending back the first images from the surface of an outer solar system body. The Dragonfly mission, a rotorcraft lander designed to fly through Titan's atmosphere and visit multiple surface locations, was approved by NASA and is targeted for launch in the late 2020s, with arrival at Titan in the mid-2030s. A journey of approximately 7 to 8 years. Let us now move to Uranus. Uranus is the third of the outer giant planets, orbiting at 19.2 astronomical units from the Sun, with a period of approximately 84 years. It is the first planet not visible to the naked eye, only discovered in 1781 by William Herschel using a telescope. At its closest, Uranus is approximately 2.57 billion kilometers from Earth. At its most distant, approximately 3.15 billion kilometers. Only one spacecraft has ever visited Uranus. Voyager 2, the same spacecraft that flew past Jupiter in 1979 and Saturn in 1981, reached Uranus in January 1986, after a journey from Earth of approximately 8.5 years, and from Saturn of approximately 4.5 years. It flew past Uranus in a matter of hours, not orbiting, simply passing through the system, and sent back the first close-up images of Uranus and its moons, before continuing outward toward Neptune. That single flyby in January 1986, 39 years ago, remains the entirety of humanity's close-up observations of Uranus. Everything we know about Uranus from spacecraft data comes from a brief flyby conducted during the Reagan administration. A dedicated Uranus orbiter, a spacecraft designed to enter orbit around Uranus rather than simply fly past, would take approximately 12 to 14 years to reach the planet on a direct trajectory. With gravity assists, optimized trajectories exist in the early 2030s that would use Jupiter flyby assistance and could reach Uranus in approximately 11 to 13 years. The 2023 Planetary Science Decadal Survey recommended a Uranus orbiter and probe as NASA's highest priority flagship mission for the coming decade. Such a mission would launch in the late 2030s at the earliest and arrive at Uranus in the late 2040s or early 2050s, well into the careers of scientists who are graduate students today, and after the retirement of most scientists currently working in the field. The communication delay to Uranus is approximately 144 to 176 minutes one way, roughly 2.5 to 3 hours for a signal to travel from Uranus to Earth. Round trip, 5 to 6 hours. A human crew at Uranus would receive responses to questions from Earth a minimum of 5 hours after asking them. The operational autonomy required would be qualitatively different from anything ever experienced by human explorers. No person on Earth could provide meaningful, real-time assistance. The crew would need to be not just capable of independent operation, but capable of independent decision-making in ways that challenge everything about how human space operations are currently organized. And getting there would take 12 to 14 years, one way, with current technology. Neptune now. Neptune is the farthest planet from the Sun, its orbit ranging from approximately 29.8 to 30.3 astronomical units over its 165-year orbital period. At its closest to Earth, Neptune is approximately 4.3 billion kilometers away. At its most distant, approximately 4.7 billion kilometers. Again, Voyager 2 is the only spacecraft to have visited Neptune. It reached Neptune in August 1989, 12 years and 23 days after its launch in August 1977. It flew past Neptune and its largest moon, Triton, before departing the solar system. That flyby, 36 years ago, remains the only close-up observation of Neptune ever made. The images from Voyager 2's Neptune flyby showed a planet of extraordinary beauty. Deep blue, intensely coloured by methane absorption of red light, with a great dark spot analogous to Jupiter's Great Red Spot, though later observed to have disappeared when Hubble Space Telescope viewed Neptune in 1994. Triton, Neptune's largest moon, was found to be geologically active. Voyager detected nitrogen geysers erupting from its south polar region. A direct Hohmann transfer to Neptune would take approximately 30 years. This is why no dedicated Neptune orbiter has ever been sent. The journey time exceeds many scientists' entire careers. With gravity assists, specifically a Jupiter flyby during favourable alignment, Neptune mission trajectories can be reduced to approximately 12 to 13 years, similar to what Voyager 2 achieved. These optimal trajectories require alignment of Jupiter and Neptune that occurs only during specific windows approximately 12 years apart, aligned with Jupiter's orbital period. If nuclear propulsion were available, nuclear thermal propulsion with roughly twice the specific impulse of chemical rockets, Neptune transit times might be reduced to approximately 8 to 10 years. With more advanced nuclear electric or fusion propulsion, potentially to 4 to 6 years. But these propulsion systems do not currently exist in flight-ready form. The communication delay to Neptune is approximately 244 to 265 minutes one way, over 4 hours for a signal to travel from Neptune to Earth. Round trip, over 8 hours. Sending a command to a spacecraft at Neptune and receiving acknowledgement that the command was received takes over 8 hours. For the Voyager 2 Neptune flyby in 1989, every command sent to the spacecraft had to be prepared days in advance because there was no possibility of real-time correction. Every maneuver was pre-planned and uploaded. The spacecraft executed its choreography automatically, while mission controllers waited hours for confirmation. A human crew at Neptune would be separated from Earth by over 8 hours of light travel time. No meaningful conversation is possible. No real-time decision support from Earth. no rescue possible on any timescale shorter than a decade. They would be the most genuinely isolated human beings in the history of the species. More isolated than any Antarctic winter overstation, more isolated than any previous human space mission, more isolated than anything our civilization has experience with. And reaching Neptune with current technology would take approximately 12 to 13 years. Let us now pull back and look at the entire picture. Mercury, 6 to 7 years with gravity assists. Venus, 3.5 to 5 months. Mars, 6 to 9 months. Jupiter, 18 months to 6 years, depending on trajectory and gravity assists. Saturn, 3 to 7 years, depending on trajectory and gravity assists. Uranus, 12 to 14 years. Neptune, 12 to 13 years with gravity assists, approximately 30 years on a minimum energy trajectory. These numbers span an extraordinary range. The fastest feasible trip to a neighbouring planet, Venus, takes about the same time as a standard pregnancy.
The journey to Neptune on a favourable trajectory takes longer than American presidents are constitutionally permitted to serve 2 terms combined. The journey to the farthest planets exceeds the length of most graduate school programs, most children's school careers from kindergarten to high school graduation, most significant phases of human life. And these times assume robotic spacecraft optimized for fuel efficiency rather than speed. For human missions, the calculus would need to change. A human crew on a 7-year journey to Mercury would experience 7 years of cumulative radiation dose, 7 years of microgravity physiological effects, 7 years of psychological isolation for a planet they cannot even land on, because Mercury's surface gravity and proximity to the Sun make landing and return with chemical propulsion essentially impractical.
A human crew on a 12-year journey to Uranus would depart Earth in one phase of their life and arrive as different people, physiologically altered by years in space, professionally outdated in some domains, separated by over 2.5 hours one-way communication delay from everyone they knew when they left. These are not abstract engineering challenges. They are statements about what it actually means to travel in this solar system, about the scale of the distances, about the difference between the solar system as a concept, a diagram on a page, a model in a museum, a list of planets learned in school, and the solar system as a physical reality that must be crossed in spacecraft with finite fuel, finite food, finite radiation shielding, and finite human endurance. Let us now talk about something that changes all of these numbers, about what different propulsion technologies could do to transit times, and what it would take to make the outer solar system accessible on human timescales. Chemical propulsion, the technology of every crewed spacecraft ever flown, uses the energy released by chemical reactions between propellant and oxidizer. Liquid oxygen and liquid hydrogen produce the highest performance of any chemical combination, with a specific impulse of approximately 450 seconds. This is the performance limit of chemical rockets. Nuclear thermal propulsion uses a nuclear reactor to heat hydrogen to extreme temperatures before expelling it through a nozzle. The higher exhaust temperature means higher exhaust velocity, means higher specific impulse, approximately 800 to 900 seconds, roughly twice chemical rockets. This doubles the velocity achievable for a given propellant mass, cutting transit times significantly. With nuclear thermal propulsion, Mars transit times could be approximately 4 months, Jupiter missions in under a year, Saturn in 2 to 3 years, Uranus and Neptune in 5 to 8 years.
Nuclear thermal propulsion was developed and ground tested in the 1960s under the NERVA program. It worked. it was never flown. The technology exists and could be revived with modern materials and engineering. Nuclear electric propulsion uses a nuclear reactor to generate electricity that powers ion engines, devices that accelerate ions to extremely high velocities using electric fields. Ion engines achieve specific impulses of thousands of seconds, far beyond chemical or nuclear thermal systems, but produce very low thrust. They accelerate slowly but continuously, building up velocity over weeks and months rather than in the brief burn of a chemical rocket. Deep Space One and Dawn are examples of spacecraft using ion propulsion, though powered by solar panels rather than reactors. A nuclear electric propulsion system could significantly reduce transit times to the outer solar system, while requiring far less propellant than chemical rockets.
The trade-off is the long acceleration period. Ion engines work best for robotic missions that can accelerate gradually over months. For human missions, very low thrust means very slow acceleration, which means the crew would experience extended periods in the early acceleration phase before reaching high velocity. Fusion propulsion, using controlled nuclear fusion to produce thrust, could, in principle, achieve specific impulses of hundreds of thousands of seconds and very high thrust simultaneously. A fusion-powered spacecraft could potentially reach Mars in weeks, Jupiter in a few months, the outer planets in a year or two. But controlled fusion is not yet achieved at practical scale for any application, let alone spacecraft propulsion. Laser or microwave-pushed light sails, large reflective surfaces pushed by beams from powerful lasers or microwave transmitters, could, in principle, accelerate small probes to significant fractions of the speed of light. The Breakthrough Starshot initiative is developing this concept for interstellar probes. At 20% of the speed of light, a probe would reach Neptune in a matter of hours. But the power requirements for pushing a meaningful payload at these velocities are extraordinary, and the technology remains far from practical application. The practical near-term change to transit times comes from nuclear thermal propulsion, an existing, tested technology that could halve or better the transit times of chemical rockets for missions to the inner and middle solar system. For the outer planets, even nuclear thermal propulsion leaves transit times in the years to decade range. Making Uranus and Neptune accessible for human exploration on timescales of a few years rather than a decade or more would require fusion propulsion or some other technology achieving specific impulses orders of magnitude beyond current capabilities. The outer solar system will remain the domain of long-journey robotic exploration for the foreseeable future of human civilization. The inner solar system, Mars, and with great difficulty Venus, is within reach of human missions using near-term technology. The gas giants are accessible for humans only on timescales that challenge institutional continuity, mission planning, and human biological resilience. Let us now talk about what it means to actually live through these transit times, what the experience of months or years in interplanetary space would be like for any human crew. The physical environment of interplanetary space is hostile in ways that accumulate over time. Radiation is the first concern. The Sun continuously emits high-energy charged particles in the solar wind and in more intense bursts during solar flares and coronal mass ejections. Galactic cosmic rays, high-energy particles from outside the solar system, penetrate spacecraft shielding more effectively than solar particles. Estimates suggest that a round-trip Mars mission would expose the crew to approximately 1 sievert of radiation, approaching or exceeding the career limits currently set by space agencies for astronauts. A round trip to Jupiter or beyond would accumulate multiple times this dose. Long-term radiation exposure increases cancer risk, and high-energy heavy ions from galactic cosmic rays cause direct cell damage in ways that produce neurological effects in animal studies. Microgravity is the second concern. Without gravity, the human body undergoes systematic changes. Bone density loss at approximately 1 to 2% per month, muscle mass loss, cardiovascular deconditioning, fluid shifts that affect vision through increased intracranial pressure, immune system changes, balance system changes. These effects are managed on the International Space Station through extensive daily exercise regimens, but they are not fully prevented. After 6 months on the ISS, astronauts typically require weeks to months of rehabilitation before full functional recovery. Psychological isolation is the third concern. A small crew confined to a spacecraft for months or years, unable to escape each other's company, unable to receive real-time social interaction from Earth, managing growing communication delays with every passing week. The psychological demands are without precedent. Antarctica winter-over crews are the best studied analogue, and they consistently show stress, interpersonal conflict, and performance decrements over the course of isolated deployments. Confinement and monotony are fourth. A spacecraft en route to Jupiter or Saturn offers no new environments, no new people, no variation in the fundamental daily circumstances. The same walls, the same crewmates, the same tasks. For 18 months in the case of Jupiter, potentially years for the outer planets. These factors together, radiation, microgravity, psychological isolation, confinement, would represent an unprecedented challenge for any human crew on a mission beyond Mars. They explain why human missions to Jupiter and beyond are not simply engineering challenges, but require solutions to biological and psychological problems that do not yet exist. And yet these challenges must ultimately be faced if human civilization intends to extend itself beyond the inner solar system. The outer planets harbor environments of extraordinary scientific interest. The potential ocean moons of Jupiter and Saturn, the hydrocarbon lakes of Titan, the mysterious interiors of the ice giants. The resources of the outer solar system, hydrogen, helium-3, water ice in quantities that dwarf anything in the inner solar system, would be significant for any long-term spacefaring civilization. The distance and the time are the obstacles, not in principle, in practice. Not because physics forbids human presence in the outer solar system, but because getting there takes so long, in conditions so harmful, at distances so far beyond any rescue or resupply, that the challenge requires technological and institutional capabilities we do not yet fully possess. The honest answer to how long it takes to fly to every planet is not a single number for each planet. It is a range, determined by launch window, trajectory choice, available propulsion, and acceptable fuel expenditure, and the ranges span months to decades. Venus in 3.5 to 5 months, Mars in 6 to 9 months, Jupiter in 18 months to 6 years, Saturn in 3 to 7 years, Uranus in 12 to 14 years, Neptune in 12 to 13 years on favourable trajectories, Mercury in 6 to 7 years despite being the closest to the Sun. These are the numbers that the solar system actually demands, not the numbers a diagram suggests. Not the numbers intuition would produce from looking at a scale model, the numbers that result from orbital mechanics, from the counterintuitive properties of moving between orbits in a gravitational field, from the choices made by real mission designers, balancing fuel, launch vehicle capability, mission duration, and scientific return. The solar system is larger than it looks, much larger. Let us talk about something that puts all of those transit times in human perspective, about what actually happened during the journeys of the spacecraft that made these trips, and what those years in transit meant for the people who built them and waited for them. The Voyager program provides the most vivid illustration. Two spacecraft, launched in August and September of 1977, were designed to take advantage of a rare planetary alignment that occurs once approximately every 176 years, a configuration in which Jupiter, Saturn, Uranus and Neptune are all positioned so that a single spacecraft can visit all four using gravity assists to redirect its trajectory from one to the next. The alignment window that made the Voyager Grand Tour possible opened in the late 1970s. The next similar opportunity will not occur until approximately 2153. The team that designed and launched Voyager knew that many of them would not live to see the mission complete. Neptune was 12 years away. Scientists in their 40s at launch would be in their 50s at Neptune. Graduate students involved in the project would be senior scientists. The mission would outlast careers, funding cycles, institutional priorities, and in some cases, the people themselves. Voyager 1 launched September 5, 1977. It reached Jupiter on March 5, 1979, 18 months later. The images were extraordinary. The first close-up views of the Jovian system, revealing the volcanic activity on Io, the complex structure of Jupiter's cloud bands, the detailed character of the Great Red Spot as a genuine rotating storm system. Scientists who had spent years working on mission planning and instrument development were seeing for the first time what they had aimed at. Then Voyager 1 used Jupiter's gravity to redirect toward Saturn. Another 20 months passed. Saturn arrival was November 12, 1980. Rings resolved into thousands of ringlets. Saturn's moon, Titan, revealed a thick orange atmosphere. Enceladus showed anomalously clean ice, suggesting geological activity. More extraordinary images, more science. Then Voyager 1 was redirected by Saturn's gravity out of the ecliptic plane, away from the remaining planets, and began its journey toward interstellar space. Its planetary science mission was complete. Voyager 2, taking a different path, reached Jupiter in July 1979. Saturn in August 1981, then continued to Uranus, arriving January 24, 1986. 8.5 years after launch. Uranus turned out to be a planet of almost featureless blue-green appearance in visible light, tilted so extremely that its poles point almost directly toward and away from the Sun. Its moons were revealed: Miranda, Ariel, Umbriel, Titania, Oberon, the first close-up images. Science teams pored over every image, every spectrum, every magnetic field measurement. Then Neptune. Another 3.5 years. August 25, 1989, 12 years after launch. The scientists who had built the instruments, who had planned the observations, who had spent a decade waiting for this data, they crowded around screens at the Jet Propulsion Laboratory in Pasadena. The first clear images of Neptune showed a brilliant blue planet with atmospheric features, a great dark spot, and high white cirrus clouds. Triton, Neptune's largest moon, was revealed as an extraordinarily alien world, with geysers and pink nitrogen ice and a thin atmosphere. Data poured back from 4.4 billion kilometers away at the speed of light, taking over 4 hours to arrive. What those scientists felt watching data arrive from the farthest place any human artifact had ever been, from a planet they had been flying toward for 12 years, is not something that any engineering specification captures. The transit time to Neptune is not just a number. It is the amount of time those scientists lived with the knowledge that their spacecraft was crossing the solar system, that the instruments they had built were still working, that the science they had waited for was getting closer with each passing month and year. The Cassini mission provides another example. Launched October 15, 1997, the team knew they had 7 years before they would see Saturn in close-up. They spent those 7 years preparing, developing and testing software, planning the orbital tour, training scientists on the instruments, refining models of Saturn's system using Hubble Space Telescope data and ground-based observations. Saturn arrival was July 1, 2004. The spacecraft had to execute its Saturn orbit insertion burn, a 96-minute engine firing that would slow the spacecraft enough to be captured by Saturn's gravity, while passing through a gap in Saturn's rings. If the burn failed, Cassini would fly past Saturn and be lost. If the spacecraft was hit by a ring particle during the ring plane crossing, the mission could end. Mission controllers at JPL waited, unable to send commands in real time because the signal travel time to Saturn was approximately 84 minutes, while Cassini executed its critical burn autonomously. Then 84 minutes of silence. Then a signal confirming successful orbit insertion. A room full of engineers and scientists erupted. The 7-year journey had worked. What followed was 13 years of orbital science at Saturn. Cassini orbited Saturn 293 times, conducted 162 targeted flybys of Saturn's moons, imaged the ring system in extraordinary detail, dropped the Huygens probe to Titan's surface, and, ultimately, revealed Enceladus as one of the most astrobiologically promising objects in the solar system, a small moon with an active ocean venting water vapor into space. The spacecraft was finally directed into Saturn's atmosphere in September 2017, 20 years after launch, 13 years after arriving at Saturn, to prevent it from potentially contaminating Titan or Enceladus with terrestrial microbes. The people who built Cassini and were in their 30s at launch were in their 50s when the mission ended. The mission outlasted careers. Graduate students became professors. Some scientists retired. Some died. The spacecraft kept orbiting. These human stories are inseparable from the transit times.
The numbers 7 years to Saturn, 12 years to Neptune are not abstractions. They are the actual spans of human life that missions consume. They are the reason mission planning requires thinking not just about technology, but about career cycles, institutional continuity, and the sustained commitment of funding agencies across multiple administrations. Let us now talk about the specific numbers that govern launch windows, about why you cannot go to any planet at any time, and what happens if you miss a window. The fundamental constraint is the synodic period, the time for two planets to return to the same relative configuration as seen from Earth. This is not the same as the orbital period of the target planet. It is the period determined by the difference in angular speeds of Earth and the target. For Mars, whose orbital period is approximately 1.88 years, the synodic period is approximately 2.135 years, about 26 months. Launch windows for Mars missions repeat approximately every 26 months. Each window is open for only a few weeks to a few months, the period during which trajectories to Mars are feasible within acceptable fuel budgets. What happens if you miss a Mars window?
you wait 26 months for the next one. This is not merely inconvenient, it fundamentally affects mission planning. If a spacecraft has a technical problem discovered a month before the launch window closes and cannot be fixed in time, the mission may be delayed by 26 months. The 2020 Mars missions, including the Perseverance rover, launched during a July to August 2020 window. The next window opened in September to October 2022. A problem that delayed the 2020 launch past the window closure would have meant waiting until 2022. For Jupiter, the synodic period is approximately 13 months. Jupiter completes about 1/12 of its orbit per year, so Earth and Jupiter return to the same relative configuration every 13 months. But the gravity assist opportunities that enable efficient trajectories to Jupiter depend on specific planetary alignments that recur much less frequently. The alignment that enabled the Voyager Grand Tour recurs every 176 years. For Saturn, the synodic period is approximately 12.5 months. But again, the most efficient trajectories, those using Jupiter gravity assists, require alignment of both Jupiter and Saturn simultaneously. These opportunities are constrained by Jupiter's 12-year period and Saturn's 29.5-year period, creating more complex scheduling requirements. For the outer planets, Jupiter is often the key. A well-timed Jupiter gravity assist can dramatically reduce the fuel required to reach Uranus or Neptune, but only if Jupiter is in the right position when the spacecraft passes through the Jovian system. Since Jupiter's period is approximately 12 years, Jupiter-enabled trajectories to the outer planets repeat on roughly 12-year cycles, with additional constraints from the target planet's own positions. The New Horizons mission to Pluto, launched January 19, 2006, required both a powerful launch vehicle and a precisely timed Jupiter gravity assist. It flew past Jupiter in February 2007, using the giant planet's gravity to add approximately 4 kilometers per second to its velocity and reduce the transit time to Pluto from approximately 14 years to approximately 9.5 years. It reached Pluto on July 14, 2015. If New Horizons had missed the Jupiter flyby opportunity, if it had launched even a few weeks later or earlier than the optimal window, it would have needed additional years to reach Pluto. The specific timing of the launch was driven by the requirement to thread both the Pluto geometry and the Jupiter flyby opportunity simultaneously. This is the practical meaning of launch windows. Not just that there are good and bad times to launch, but that the entire architecture of a mission, the trajectory chosen, the gravity assists used, the transit time, the arrival geometry, all depend on the specific date of launch within the window. Missing the window doesn't just delay the mission, it often requires entirely redesigning the trajectory, potentially changing the gravity assists, potentially adding years to the transit time, potentially making the mission infeasible within the fuel budget. Launch windows are not scheduling conveniences. They are constraints imposed by orbital mechanics on every mission in the solar system. Let us now talk about the specific experience of distance in a way that the transit time numbers alone do not capture. About what the communication delay actually means operationally, and how it changes the nature of mission control as distances grow.
At Earth's surface, communication is essentially instantaneous. Call someone in another country? The signal travels at the speed of light through undersea cables or via satellite, crossing the globe in under a second. The imperceptible delay does not affect conversation. At the Moon, the one-way signal travel time is approximately 1.3 seconds. A round-trip delay of 2.6 seconds, long enough to notice in conversation. There is a reason live transmissions from the Moon during Apollo had slightly awkward pacing, but short enough to permit real-time exchange of information. When Apollo 13 suffered its oxygen tank explosion in April 1970, mission controllers could exchange information with the crew in near real time, working through solutions collaboratively. At Mars, the minimum one-way communication delay is approximately 3 minutes, maximum approximately 22 minutes. A round trip from 3 minutes to 22 minutes means from 6 minutes to 44 minutes per exchange. For any real-time crisis, mission controllers are receiving information that is 3 to 22 minutes old, and any advice they send takes another 3 to 22 minutes to arrive. The rovers on Mars, Spirit, Opportunity, Curiosity, Perseverance, are operated on a cycle precisely because real-time control is impossible. Controllers at JPL receive data from the rover, images, instrument readings, status information, and spend hours or a day planning the next set of commands. The command sequence is uploaded and the rover executes it autonomously while controllers wait for the next batch of data. When Perseverance landed in February 2021, the entire landing sequence, the entry, descent and landing, was pre-programmed. Mission controllers at JPL could only watch a simulation running in parallel on Earth, while the actual landing happened autonomously on Mars, with no ability to intervene. By the time the signal confirming touchdown arrived at Earth, the landing had already succeeded or failed 11 minutes earlier. The celebration that erupted in mission control when the confirmation signal arrived was celebrating an event that had already concluded. They were just receiving the news. At Jupiter, with one-way delays of 33 to 54 minutes, this autonomous operation becomes even more critical. The Galileo spacecraft at Jupiter executed its science operations and orbital maneuvers with only periodic command uploads from Earth, operating largely independently between uplinks. When something unexpected happened, an anomaly, an unexpected observation, mission controllers received the information 33 to 54 minutes after it occurred and sent their response 33 to 54 minutes after that. The minimum response time to any event was over an hour. At Saturn, 68 to 95 minutes one way. The time between an event and the ability to respond is measured in hours. Cassini executed its ring plane crossings, its Titan flybys, its Enceladus encounters, all autonomously. The spacecraft was programmed with enough intelligence to protect itself. If it detected a hazard, it could execute pre-planned contingency responses without waiting for human authorization from Earth. At Uranus and Neptune, over 2 to 4 hours one way, a spacecraft must be essentially fully autonomous. Every planned maneuver, every observation sequence, every contingency response must be pre-planned and uploaded. Mission controllers observe what happened, not what is happening. This growing communication delay is not just an operational inconvenience. It is a fundamental change in the relationship between human mission controllers and spacecraft. At Earth orbit, human reflexes and judgment operate in real time. At Mars, human experts can provide analysis and guidance, but on a timescale of hours, not seconds. At Jupiter and beyond, the spacecraft must be intelligent enough to respond to its own environment on timescales shorter than the round-trip communication delay. For human crews in the outer solar system, the communication delay changes the nature of their relationship to Earth in a profound way. A crew at Mars can have a conversation with Earth. It is slow, with 6 to 44 minutes between exchanges, but it is possible to exchange complete thoughts and receive responses within a shift. A crew at Jupiter is having exchanges that take over an hour,
for each round trip, something closer to correspondence than conversation. A crew at Saturn waits 2.5 to 3 hours per round trip. At Neptune, over 8 hours. These delays are not merely communication inconveniences, they are isolation. A crew at Neptune cannot call home and receive a response until the next day, cannot receive medical consultation in any meaningful real-time sense, cannot receive mission support on any timescale relevant to a fast-moving operational situation. Everything they face alone. Let us now talk about something that requires putting all of the previous numbers together in a specific and confronting way, about what a comprehensive human exploration program of the solar system would actually look like in terms of mission durations and what it demands of the human beings who would undertake it. A human mission to Venus, the easiest destination after the Moon, would have a transit of approximately 3.5 to 5 months each way, with a brief period at Venus between transit legs totaling perhaps 1 to 2 months for a flyby mission or indefinite for an orbital mission. The total mission would be approximately 8 months to a year. The radiation environment at Venus orbit, closer to the Sun than Earth, would expose the crew to higher solar energetic particle flux than at Earth. The possibility of landing on Venus' surface is essentially nil for any crewed mission with foreseeable technology. The surface temperature of 465 degrees Celsius and atmospheric pressure 90 times Earth's would destroy any crewed landing vehicle. A Venus atmospheric mission, a crewed airship floating in the cloud deck at 50 kilometers altitude, where temperatures and pressures are roughly Earth-like, is theoretically possible and has been studied. A human mission to Mars, the most discussed near-term human destination, would involve approximately 6 to 9 months transit each way, and approximately 18 months on the surface waiting for the return window, totaling approximately 2.5 to 3 years. During this time, the crew would accumulate radiation dose approaching or exceeding current career limits, undergo significant physiological changes from microgravity, and operate with communication delays of 3 to 44 minutes each way. A human mission to the asteroid belt, perhaps to a large asteroid like Ceres, would involve transit times of approximately 3 to 4 years round trip, with communication delays of 15 to 30 minutes each way. A human mission to Jupiter orbit, perhaps to observe Jupiter's moons from orbit, would involve transit times of 18 months to 3 years each way, totaling perhaps 3 to 6 years for a mission that returned to Earth. Communication delays of 33 to 54 minutes each way. Radiation environment in Jupiter's magnetic field requiring substantial shielding. The crew would return to Earth physiologically altered by years in space, with accumulated radiation doses substantially exceeding current guidelines. A human mission to the Jovian moons, specifically Europa or Ganymede, would require landing on a moon in one of the most intense radiation environments in the solar system outside the Sun itself. The radiation dose rate on Europa's surface is approximately 5,400 millisieverts per day, enough to cause acute radiation sickness in a week and be lethal in a month without extreme shielding. Any crewed Europa surface mission would require radiation shielding that would dramatically add to mission mass. A human mission to Saturn orbit, perhaps to Titan, would involve transit times of 3 to 7 years each way, communication delays of over 2 hours each way, and mission durations potentially exceeding 15 to 20 years for a full orbital mission. The crew would return, if they returned, to a world that had changed substantially in their absence. Children born when they left would be teenagers when they returned. A human mission to Uranus would take approximately 12 to 14 years one way. Round trip, if a return were even planned, perhaps 25 to 30 years. A person who left Earth at age 30 would return at age 55 to 60 at best, after spending most of their working life in interplanetary space. A human mission to Neptune would be similar or longer, 12 to 13 years one way, over 8 hours of communication delay each way, requiring propulsion and life support systems that sustain human life for decades without resupply. These mission durations place human exploration of the outer solar system in a different category from anything previously contemplated. Not a challenging mission, not an extremely long mission, a multi-generational commitment, at least from the perspective of the crew members who would dedicate their careers and significant portions of their lives to a single mission. The institutional challenge is equally daunting. A mission to Neptune that takes 12 to 13 years each way requires an institution to maintain its mission focus and funding for 25 to 30 years or more, across multiple government administrations, multiple budget cycles, multiple shifts in national priorities. No human space mission has ever sustained this kind of institutional continuity in the crewed spaceflight context. The Apollo program, from its Kennedy speech in 1961 to the final Apollo 17 landing in 1972, spanned 11 years. Sustaining a crewed Neptune mission for twice that duration would require an unprecedented level of political and institutional commitment. These are not arguments against outer solar system human exploration. They are arguments for taking seriously how different it is from anything attempted to date, and for developing the propulsion technologies that could reduce these transit times to something more compatible with human careers and institutional commitments. Let us now talk about something that is active and ongoing, about missions currently in flight, missions in development, and what the next few decades of solar system exploration look like in terms of transit times and destinations. The Parker Solar Probe, launched in August 2018, has been using Venus gravity assists to progressively lower its orbit and bring it closer to the Sun. By 2025, it will reach its closest perihelion, approximately 6.1 million kilometers from the Sun's surface, well within Mercury's orbit. It is not traveling to a planet, but toward the Sun itself, and it does so on a spiraling trajectory that uses repeated Venus flybys over years to remove orbital energy. Total mission duration over 7 years. The Bepi-Colombo mission to Mercury, launched October 2018, is executing its complex 9-flyby trajectory and will arrive at Mercury in late 2025, approximately 7 years after launch. It carries 2 orbiters, one from ESA and one from JAXA, that will separate and enter different Mercury orbits. The JUICE mission, Jupiter Icy Moons Explorer, was launched by ESA in April 2023. It will use gravity assists from Earth, Venus, and Earth again before reaching Jupiter in July 2031, approximately 8 years after launch. It will then orbit Jupiter and conduct flybys of Europa, Callisto, and Ganymede before eventually entering orbit around Ganymede in 2034, becoming the first spacecraft to orbit a moon of another planet other than the Moon. Total mission from launch to Ganymede orbit, approximately 11 years. NASA's Europa Clipper mission launched in October 2024. It will fly past Mars and then Earth for gravity assists before reaching Jupiter in April 2030, approximately 5.5 years after launch. It will then conduct approximately 50 flybys of Europa over several years, studying the Moon's subsurface ocean. The Dragonfly mission, a rotorcraft lander for Titan, was approved by NASA and is targeted for launch in the late 2020s, with arrival at Titan approximately 7 to 8 years later. It will fly through Titan's thick atmosphere, visiting multiple surface locations over its operational lifetime. A proposed Uranus orbiter and probe, the highest priority flagship mission recommended by the 2023 Planetary Science Decadal Survey, could launch in the mid-2030s, using a launch window that enables a Jupiter gravity assist, arriving at Uranus approximately 13 years later in the late 2040s or early 2050s. It would be the first dedicated Uranus mission since Voyager 2's flyby in 1986. A proposed Neptune orbiter, possibly combined with a Triton lander, would face similar trajectory constraints and similar transit times. A mission launched in the 2030s on a favourable trajectory might arrive at Neptune in the 2040s or 2050s. The pattern in these missions is striking. The transit times for outer solar system missions are measured in years to decades. A mission launched today will arrive at its destination after most of the people currently excited about it have moved on to other projects or careers. The scientists who would lead the Jupiter missions currently in flight were graduate students when those missions were approved. The scientists who will lead data analysis for a Uranus orbiter arriving in the 2040s are now beginning their careers. This is not unusual in planetary science. It is the nature of the enterprise. But it is a feature of the solar system's scale that is not captured by any diagram or any list of planet names and distances. The solar system is so large that exploring it seriously requires institutional commitments spanning generations of scientists. Not metaphorically, literally. Let us now talk about something that takes the transit times and puts them in the most intimate possible human context. About what you would see and experience and feel during each leg of an interplanetary journey if you were the human making it. Imagine you were on a spacecraft leaving Earth for Mars on a 7-month transit. The first thing you notice after the rocket burn that puts you on the transfer trajectory is the shrinking of Earth. In the first hour, it is already smaller. In the first day, it fits within the span of your outstretched hand. In the first week, it is a bright blue dot, still recognizable but clearly reduced. In the first month, it is a blue point of light, distinct from the stars, but only if you know where to look. Your destination, Mars, is not yet growing. It is too small and too far to show visible change for months. You are between 2 points, neither of which provides any sense of progress. You fly through empty space at approximately 30 kilometers per second, fast enough to cross a continent in a minute. And the solar system is so large that this extraordinary speed produces no visible change in your environment from one day to the next. The Sun gets slightly smaller as you move outward from Earth's orbit. Not dramatically, you're moving from 1.0 to roughly 1.52 astronomical units, a factor of 1.5 in distance. The sunlight gets somewhat dimmer, not dark, still bright by Earth's surface standards on a clear day, but measurably reduced. Shadows are slightly less sharp. Surfaces in direct sunlight warm slightly less efficiently. The stars are constant. They show no parallax at the scale of your movement within the solar system. They are the same patterns you knew from Earth. Orion, the Big Dipper, the Southern Cross if you're in that orientation. Familiar, unchanged, offering no sense of motion. The only sign of progress, week after week, is the growing communication delay. In the first week, calling Earth produces a response in minutes. You can still have something approaching a conversation, though stilted by the delay. In the first month, the delay is 5 to 10 minutes each way. By month 3, it could be 15 minutes. By month 6, approaching Mars, perhaps 18 to 20 minutes. Each exchange with Earth becomes increasingly like correspondence. You ask a question and wait half an hour or more for an answer. People on Earth are living their lives. News happens, seasons change, someone gets married, someone dies. You receive these updates at light speed, 18 minutes delayed, while you float in a metal can between planets, unable to attend, unable to respond in real time, unable to do anything except continue the transit. After 5 to 6 months, Mars begins to resolve from a reddish point of light into a disk. Then features become visible: the polar ice caps, the dark markings of ancient geological features, the atmospheric haze. The disk grows over weeks. Entry into Mars orbit produces a dramatic change in apparent motion. The planet now fills a significant portion of your view. The orange-red surface is visible in detail. But you have been in space for 6 to 7 months. Your muscles are weaker. Your bones have lost density. Your cardiovascular system has deconditioned. Getting up from your seat and walking in Martian gravity, 0.38 of Earth's, will feel different from both Earth and the weightlessness you have adapted to. You will need weeks to readapt. Now imagine the same journey, but to Jupiter, 18 months to 2 years. After a few months, the Sun is noticeably smaller. After a year, it is roughly 1/3 the angular size it appears from Earth. Still bright, still dominant, but diminished. The inner solar system has shrunk behind you. Earth is an invisible point. Even the asteroid belt asteroids you pass near are invisible without instruments. The total darkness and total silence of deep space, broken only by the hum of spacecraft systems, is present for months, years. The same crewmates, the same walls, the same schedule. Growing communication delays, 33 minutes minimum each way at Jupiter, so by the time you approach your destination, exchanges with Earth take over an hour per round trip. Jupiter finally grows. It goes from a point to a disk to a planet. Then its moons become visible without instruments, the 4 Galilean moons, Io, Europa, Ganymede and Callisto, each distinctive. Jupiter's cloud bands, the great red spot as a genuine oval feature in the southern hemisphere. The radiation belts you are flying through, invisible to the eye, but steadily depositing energetic particles in your body, in the instruments, in the spacecraft structure. After 18 months in space, your body has been altered in ways that cannot be fully quantified until you return to a gravitational environment. Your radiation dose is substantial. Your physiological systems have adapted to weightlessness in ways that will require months of rehabilitation on return. You have received news from Earth 33 to 54 minutes late for months. Your social connections have attenuated. The world you left is a year and a half older. And this is the near-term destination. Jupiter, which the Voyager probes reached in 18 to 23 months, is considered accessible by the standards of the outer solar system. Now Saturn, 3 to 7 years. 3 years of transit in the shorter cases, 7 in the longer. Arriving at a distance where the Sun appears as a bright but clearly diminished star, not the blazing disk of Earth's sky, not even the smaller but still dominant disk visible from Jupiter, but a star that is much brighter than any other star, providing light that is about 1% of what Earth's surface receives, enough to see by, but not enough to feel warmth on skin. Saturn appears. Rings. actually visible rings, tilted at various angles depending on the orbital geometry. The moons, dozens of them, each with its own character. Titan's orange haze, Enceladus's brilliant white ice. The extraordinary visual of Saturn hanging in space, ringed, enormous, entirely unlike anything in human visual experience. You have been in space for 3 to 7 years. Your life on Earth is a distant memory in many practical senses. People you knew have moved. Children you knew have grown. You have missed years of your own children's lives. The world has had elections, recessions, technological changes. You have read about them all in messages that arrived 68 to 95 minutes delayed. The communication delay has by now made conversation with Earth essentially impossible in any meaningful real-time sense. Each exchange, a question and its response, takes 2.5 to 3 hours minimum. You communicate as though writing letters. You have learned to formulate complete thoughts, to not wait for responses before continuing, to accept that the conversation is asynchronous in a way that no human relationship was designed to handle. These are the transit times. These are what they mean, translated from numbers into experience. The solar system is not large in the way that a big country or a big ocean is large. It is large in the way that makes the concept of large break down as a useful descriptor. It is large enough that reaching its outer parts requires investments of human time that compete with the length of careers, that accumulate physiological costs that exceed current medical understanding to manage, that produce communication delays that strain the concept of connection to its breaking point. And this is the solar system, a single star system among hundreds of billions in the galaxy. The galaxy is separated from the nearest other galaxy by 2.5 million light-years. The nearest star is 4.37 light-years away, a distance that our fastest spacecraft would take 73,000 years to cover. The transit times to the planets, spanning months to decades, are not large compared to the scales of the universe. They are the smallest interplanetary distances. The minimum travel times for the minimum journeys. Everything beyond is larger still. Let us now talk about what the trajectory planning actually looks like in practice, about the specific calculations and tools that allow mission designers to find paths through the solar system, and how the complexity of real trajectory design goes far beyond the simplified Hohmann transfer picture. Real trajectory design is an optimization problem with many variables and many constraints. The variables include the launch date and time, the launch azimuth, the trajectory type, direct, with gravity assists, with multiple burns, the timing of any intermediate flybys, the approach geometry at the destination, and the desired final orbit if an orbiter rather than flyby. The constraints include the available launch vehicle performance, the fuel capacity of the spacecraft, the required arrival time relative to scientific objectives and operational windows, and the communication geometry at various points in the mission. Mission designers use software tools, primarily the GMAT, General Mission Analysis tool, developed by NASA, and JPL's own trajectory optimization tools to search through this high-dimensional space of possibilities. They look for trajectories that meet all constraints while optimizing some objective, usually minimizing fuel consumption or transit time or some combination. The fundamental mathematical framework is celestial mechanics, the application of Newton's laws of gravity to the motion of bodies in the solar system. Each planet exerts a gravitational force on the spacecraft that depends on the planet's mass and the distance between them. Near a planet, the planet's gravity dominates, and the spacecraft follows a conic section, an ellipse, parabola, or hyperbola around the planet. Far from any planet, the Sun's gravity dominates, and the spacecraft follows an ellipse around the Sun. Gravity assist maneuvers, the flybys that add or remove velocity, involve transitioning between these two regimes. A spacecraft approaching a planet is deflected by the planet's gravity, following a hyperbolic trajectory around it. If the geometry is right, the spacecraft can emerge from the planet's gravitational sphere of influence with a different velocity relative to the Sun than it had when it entered. The planet loses a tiny amount of orbital energy to the spacecraft through this interaction, but the planet is so massive that the effect on its orbit is completely negligible. The pork chop plot is a visualization tool that mission designers use to survey launch opportunities. It is a contour map with launch date on one axis and arrival date on the other, with contour lines showing the required propulsion energy, called C3, for each combination. The plots show the launch window structure. The favourable periods appear as low-energy valleys in the C3 landscape and allow designers to identify candidate trajectories for detailed optimization. For a Mars mission, pork chop plots clearly show the approximately 26-month spacing between launch windows, the variation in required energy from one window to the next, and the trade-offs between launch date and arrival date within a single window. Early in a window, earlier launches allow more time for transit, arriving on a lower energy trajectory. Late in a window, launches must take higher energy trajectories to reach Mars in time before the geometry closes. For the outer planets, pork chop plots for gravity assist trajectories show the much more complex structure of opportunities. A Jupiter flyby trajectory to Saturn requires alignment of both Jupiter and Saturn, producing a three-dimensional problem in which the contour structure is more complex and the favourable trajectories rarer. The Cassini mission trajectory required years of trajectory optimization work to find a path that met all constraints within the available launch vehicle capability. The Messenger trajectory to Mercury, the one that required 6.6 years and multiple gravity assists, was found by trajectory designers who were essentially searching for paths that could bleed off enough velocity through planetary flybys to allow Mercury orbit insertion without exceeding the spacecraft's fuel capacity. The solution they found was not obvious. It required Venus flybys and Mercury flybys timed precisely to produce the needed velocity changes, arriving at Mercury orbit after 6 years with exactly enough fuel remaining for orbit insertion and the science mission. The New Horizons trajectory to Pluto required careful timing of a Jupiter gravity assist to reduce transit time from approximately 14 years to approximately 9.5 years, while also ensuring arrival geometry at Pluto that allowed maximum science return during the single flyby. All of this optimization work, the months and years of trajectory design, is what translates the physical constraints of the solar system into the specific transit times that appear in mission plans. The transit times are not arbitrary. They are the result of finding feasible paths through a high-dimensional space of possibilities, constrained by orbital mechanics, fuel budgets, launch vehicle capabilities, and scientific objectives. The numbers, 7 months to Mars, 7 years to Mercury, 12 years to Neptune, are the minimum or near minimum time that the physics and engineering constraints allow. They represent the best that human ingenuity can achieve within the laws of nature as they are. Let us now talk about something that places all of this in a broader context, about what the transit times to the planets tell us about the place humanity currently occupies in the history of space exploration, and what they imply about the future. In 60 years of spaceflight, humanity has sent spacecraft to every planet in the solar system. We have orbited Mercury, Venus, Earth, Mars, Jupiter, Saturn, and dwarf planets including Ceres and Pluto. We have flown past Uranus and Neptune. We have landed on the Moon, Mars, Venus, Titan, and multiple asteroids. We have sent probes into the atmospheres of Jupiter and Titan. We have operated rovers on the Moon and Mars. We have sent spacecraft beyond the heliopause into interstellar space. This is an extraordinary achievement in the context of the 60 years during which it happened. It represents human civilization extending its observational reach to the entire solar system within 2 human generations. But the transit times reveal how this achievement was structured. The planets accessible on timescales of months, the Moon, Venus, Mars, are the ones we have explored most thoroughly and most repeatedly. The planets accessible on timescales of years, Jupiter, Saturn, have been visited by orbiters and atmospheric probes that operated for years. The planets accessible only on timescales of a decade or more, Uranus, Neptune, have been visited once each by a single flyby, with all close-up knowledge of those planets dating from 1986 and 1989, respectively. The transit times are the primary determinant of how well explored each destination is. Close and fast means repeatedly visited and thoroughly studied. Distant and slow means barely glimpsed. The solar system that humanity knows well, Earth, Moon, Mars, and to a lesser extent Venus and the Jupiter system, is the solar system accessible within transit times of months to a couple of years. The solar system beyond that, the ice giants, the Kuiper belt, the outer reaches of the heliosphere, is known primarily through the data returned by single flybys conducted decades ago with instruments that predate modern technology. What would we find if we sent a modern orbiter to Uranus with the instruments available today? What would a lander on Triton reveal? What does the composition of Neptune's deep atmosphere tell us about the formation of the solar system? These questions remain unanswered because the transit time to their answers is 12 to 14 years, a commitment that has not yet been made for a dedicated Uranus or Neptune mission. The recommended Uranus orbiter and probe, if approved and launched in the mid-2030s, would arrive in the late 2040s. The scientists advocating for it now will be senior or retired scientists when the spacecraft arrives. Their graduate students, not yet in graduate school, will be the ones doing the data analysis. This is what transit time means at the scale of the outer solar system. Not a logistical inconvenience, a generational commitment. The future of solar system exploration, if propulsion technology remains broadly constant, involves increasingly sophisticated robotic missions to the outer solar system on timescales of a decade or more each, with human exploration likely limited to the inner solar system on timescales of years. Enabling human exploration of the outer solar system would require propulsion advances that compress transit times from 12 to 14 years to something closer to 3 to 5 years, a factor of 3 to 4 improvement that would require nuclear or advanced electric propulsion at minimum, and possibly fusion propulsion. Whether those propulsion advances happen, and on what timescale, will determine the scope of human direct experience of the solar system over the next century. With chemical propulsion, human beings will reach Mars and possibly the asteroid belt within this century. With nuclear thermal propulsion, the Jupiter system becomes accessible to human missions within the century. With fusion or other advanced propulsion, the outer solar system opens. The transit times are not fixed facts. They are the current answer to the question of how long it takes to fly to the planets, given the propulsion technology that exists. Different propulsion technologies give different answers. But in the meantime, the solar system as it is accessible today has these dimensions: months to the inner planets, years to the gas giants, decades to the ice giants. Each measured not just in distance, but in human time, in careers and generations, and the sustained commitments of institutions. The Voyager spacecraft are still travelling. Launched 47 years ago, they have left the solar system and are now in interstellar space, the first human artifacts to cross that boundary. They move at 17 kilometers per second and will not pass within a few light years of any other star for tens of thousands of years. The transit time to the nearest star, Alpha Centauri, at Voyager's speed, is approximately 73,000 years. The planets, with their transit times of months to decades, are not the end of the challenge. They are the beginning. Let us talk about something that takes everything we have established and makes it concrete in a different way. About what it actually feels like to track a spacecraft on a multi-year journey, and what the people at Mission Control experience that no news coverage of a space mission fully conveys. The Jet Propulsion Laboratory in Pasadena, California, maintains continuous contact with every spacecraft JPL operates, from the Mars rovers to the outer solar system missions to the Voyagers in interstellar space. The Deep Space Network, a global array of large radio antennas at Goldstone in California, Madrid in Spain, and Canberra in Australia, is the infrastructure that makes this possible. The 3 stations are spaced roughly 120 degrees apart in longitude, so that as Earth rotates, at least one antenna always has line-of-sight contact with any spacecraft anywhere in the solar system. For spacecraft in the outer solar system, contact sessions are planned days or weeks in advance. The available antenna time on the Deep Space Network is a limited resource shared among dozens of active missions. Every spacecraft must compete for time on the large antennas, the 70-meter dishes that can detect the faint signals from distant spacecraft. A spacecraft at Neptune, transmitting at full power, produces a signal at Earth so faint that it requires the largest available antennas and hours of integration time to accumulate enough signal for meaningful data return. The downlink data rate from distant spacecraft is painfully slow by terrestrial standards. Voyager 1, now at approximately 24 billion kilometers from Earth, transmits at approximately 160 bits per second with the 70-meter antennas. This is not 160 kilobits or megabits, 160 bits per second. A single uncompressed image of modest resolution would take days to download at this rate. The engineers who designed Voyager built sophisticated data compression and image processing algorithms that reduce the data volume to what could be transmitted in reasonable time. Cassini at Saturn, much closer and with a more powerful transmitter, achieved data rates up to approximately 142,000 bits per second, fast enough to return significant volumes of data, but still far below what terrestrial networks take for granted. What this means practically, the science return from any given spacecraft is throttled by the communication bandwidth available. Mission scientists must prioritize which observations get transmitted first, which images are compressed more aggressively, which data products are down-sampled to fit within the available rate. Planning the observation sequence and the data prioritization is a continuous negotiation between science objectives and communication constraints. For the Mars rovers, whose data rates are higher, Mars Reconnaissance Orbiter acts as a relay, providing substantially higher bandwidth than direct Earth communication. This is less constraining. But for the outer solar system, the bandwidth limitation is a fundamental fact of the mission. Cassini returned the equivalent of approximately 635 gigabytes of data over 13 years at Saturn. An iPhone today can hold more than that. The entire data return from 13 years of Saturn orbital science fits on a modern consumer hard drive.
Each mission has a team of flight controllers, mission planners, science team members, and operations staff who work in shifts to maintain continuous operation. For a spacecraft at Saturn, this team has been living with their spacecraft for years, following its orbit, planning its maneuvers, processing its data, responding to anomalies. They develop a relationship with the spacecraft that is difficult to describe to outsiders. When Cassini's mission ended in September 2017, when the spacecraft was deliberately directed into Saturn's atmosphere to prevent contaminating the moons, the event was widely reported as an emotional one for the team. Not because the spacecraft had personalities or feelings, but because the team had spent 20 years with it. Engineers who had been young when they worked on Cassini's design were middle-aged when it ended. The spacecraft had been a continuous presence in their professional lives for 2 decades. Its loss, even planned, even scientifically motivated, was felt. This human dimension of long transit times and long missions is rarely captured in technical discussions of solar system exploration. The transit times are not just numbers in an orbital mechanics calculation. They are the years of people's lives spent working on missions that may not return significant data for years after launch. Building an instrument for a mission to Jupiter, knowing that it will not be at Jupiter for 5 to 8 years, requires a specific kind of commitment to a project that will outlast the enthusiasm of the moment, that will require sustained attention during years of transit when nothing spectacular is happening. Let us now talk about something that illuminates transit times from a different angle, about the history of solar system exploration organized by speed, and what each generation of spacecraft revealed as propulsion and trajectory design improved. The Pioneer probes of the early 1970s were the first spacecraft to cross the asteroid belt and reach the outer solar system. Pioneer 10, launched March 2, 1972, crossed the asteroid belt without incident, demonstrating that the belt was not the hazardous obstacle some had feared, and reached Jupiter in December 1973. Pioneer 11 followed and was redirected to Saturn, arriving September 1979. These spacecraft were limited. Their instruments were primitive by later standards. Their cameras could only capture low-resolution images. But they were first. They proved it could be done. They established that Jupiter's radiation belts were intense but survivable for spacecraft electronics with adequate shielding. They measured the solar wind at distances far beyond Earth. They returned the first close-up images of Jupiter and Saturn. Pioneer 10 was the first human artifact to achieve escape velocity from the solar system. On June 13, 1983, it crossed the orbit of Neptune, at the time the outermost planet, with Pluto's orbital eccentricity placing it inside Neptune's orbit during this period, and entered the realm of the outer heliosphere. It continued transmitting until 2003, when its power supply declined too far to sustain communication. It is now approximately 126 astronomical units from the Sun, heading toward the general direction of the star Aldebaran in Taurus, which it will approach in approximately 2 million years. Pioneer 11 ceased transmitting in 1995 as its power supply declined, heading toward the constellation of Aquila. The Voyager spacecraft, launched in 1977, represented a quantum leap in capability. Their cameras, spectrometers, plasma wave instruments and magnetometers returned data that transformed our understanding of the outer solar system. The Voyager images of Io's active volcanoes, Europa's cracked ice surface, Saturn's ring structure, Uranus's magnetic field tilted almost perpendicular to its orbit, Neptune's great dark spot, and Triton's geysers. These images defined how humanity thought about the outer solar system for decades. And the Voyagers survived. Not just the transit, not just the primary missions. They are still operating today, 47 years after launch. Voyager 1 is the most distant human artifact ever, over 24 billion kilometers from Earth. Voyager 2 is approximately 20 billion kilometers away in a different direction. Both are in interstellar space, past the heliopause, the boundary where the Sun's solar wind yields to the interstellar medium. Both still transmit scientific data. Both still communicate with Earth daily via the Deep Space Network. The Galileo spacecraft, launched in 1989 and arriving at Jupiter in 1995, was the first Jupiter orbiter.
It spent 8 years in orbit, until 2003, conducting repeated flybys of the Galilean moons and making fundamental discoveries. Its atmospheric probe, released before Jupiter orbit insertion, descended into Jupiter's atmosphere and survived for about an hour, transmitting measurements of temperature, pressure, and composition before being crushed by the increasing pressure at depth. The Galileo data confirmed the presence of a subsurface ocean on Europa, the first evidence for a liquid water ocean beyond Earth. The Cassini-Huygens mission at Saturn revealed a system of extraordinary complexity and scientific richness. Cassini discovered liquid lakes on Titan, the only known bodies of stable surface liquid in the solar system other than Earth's oceans, though composed of liquid methane and ethane rather than water.
It discovered the plumes of Enceladus, water vapor jets erupting from fractures in the South Polar region, carrying organic molecules, hydrogen, and other materials from the subsurface ocean into space. Enceladus became one of the highest priority targets for astrobiology, a small moon with an active ocean that could potentially harbour life. Each of these missions was made possible by specific transit times, by the years it took to reach their destinations, enabled by specific launch windows, specific trajectory choices, specific propulsion capabilities. The New Horizons mission to Pluto, launched January 2006 and arriving July 2015, demonstrated what could be achieved with a 9.5-year transit to the outer solar system, and revealed Pluto as an unexpectedly geologically active world with mountains of water ice, nitrogen ice plains, a hazy nitrogen atmosphere, and a heart-shaped geological feature that captured global attention.
The single flyby, the only close-up observation of Pluto ever made, lasted hours. Everything we know about Pluto from spacecraft data comes from those hours of flyby. New Horizons continue beyond Pluto, performing a flyby of the Kuiper Belt object Arrokoth on January 1, 2019, 13 years and 3 months after launch. Arrokoth, at approximately 44 astronomical units from the Sun, is the most distant object ever visited by a spacecraft. It revealed a pristine contact binary, 2 lobes that gently coalesced in the early solar system, providing insights into planetary formation processes. New Horizons is still operating, heading outward, conducting measurements of the outer heliosphere as it joins Voyager in exploring the frontier beyond the planets. Each of these missions represents a different point on the spectrum of transit times. Together, they constitute humanity's observational knowledge of the outer solar system, accumulated over 50 years of missions, each with its own transit time, its own launch window, its own trajectory, its own period of quiet cruise between significant milestones. Let us now talk about dwarf planets and what their transit times say about the structure of the solar system beyond the classical planets. Pluto, orbiting at an average distance of approximately 39.5 astronomical units, was reached by New Horizons in 9.5 years, enabled by the Jupiter gravity assist. Without that assist, the transit would have been approximately 14 years. Ceres, the largest object in the asteroid belt, at approximately 2.77 astronomical units, was reached by the Dawn spacecraft in approximately 3.75 years, after a journey that included Mars gravity assist and years of ion propulsion acceleration. Eris, the most massive known dwarf planet, at approximately 96 astronomical units from the Sun at its current position. Beyond its perihelion distance of 38 astronomical units, has never been visited by any spacecraft. A mission to Eris would require extraordinarily long transit times, potentially 20 to 30 years, even with gravity assists. The orbital mechanics for such a mission have been studied, but no such mission has been funded or approved. Sedna, a distant trans-Neptunian object orbiting at between 76 and 937 astronomical units, with a period of approximately 11,400 years, would require transit times of decades to centuries to reach at any plausible spacecraft velocity. It represents the outer reaches of the solar system's scattered disk, a region thought to be disturbed by encounters with passing stars, and possibly influenced by a hypothetical distant planet, Planet 9, that has been proposed based on orbital anomalies of distant Kuiper Belt objects. The Oort cloud, the theoretical spherical halo of cometary bodies extending from approximately 2,000 to 100,000 or more astronomical units, is completely inaccessible to spacecraft on any trajectory achievable with current or near-future technology. At Voyager's velocity, crossing the inner Oort cloud would take thousands of years. The solar system as a physical entity extends far beyond what any spacecraft has visited. The classical planets, the dwarf planets, the asteroid belt, the Kuiper belt, these are the populated inner disk. Beyond lies a vast outer region that is largely unexplored and for now unexplorable on any meaningful timescale. Transit times to the planets, as long as they are the accessible portion of the full solar system transit challenge.
The truly outer solar system, the Oort cloud, the scattered disk, the distant dwarf planets, requires either orders of magnitude improvement in propulsion or the acceptance that these regions will remain known only through indirect astronomical observation for the foreseeable future. Let us now talk about something that is both concrete and rarely discussed, about what happens to a spacecraft during the years of transit, and how the engineering of keeping a spacecraft alive over multi-year journeys determines what is possible. A spacecraft on a 12-year journey to Neptune must function reliably for that entire duration. Every system, power, propulsion, communications, attitude control, science instruments, must continue working in the radiation and thermal environment of deep space for over a decade. Power is the first constraint.
Solar panels, which work well in the inner solar system where sunlight is plentiful, become inadequate in the outer solar system, where sunlight is only 1% or so of the intensity at Earth. The Cassini spacecraft used radioisotope thermoelectric generators, RTGs, devices that convert the heat from radioactive decay of plutonium-238 into electricity. The New Horizons spacecraft similarly uses RTGs. The Voyager spacecraft use RTGs that have been operating for 47 years and still generate enough power to operate a few instruments, though far less than at launch. RTG technology is reliable, radioactive decay proceeds predictably, and the thermoelectric conversion is a solid-state process with no moving parts. But plutonium-238 is difficult to produce. The US ceased producing it in the 1980s and had to restart production in recent years to ensure supply for future missions. Each mission requires significant quantities of plutonium, and the limited production capacity constrains how many outer solar system missions can fly simultaneously. Thermal management over a 12-year transit requires spacecraft capable of surviving the full range from warm near Earth to cold in the outer solar system. Components must operate reliably across temperature ranges of hundreds of degrees. Thermal blankets, heaters, and radiators must be designed to maintain critical systems within their operating temperature ranges throughout the full mission profile. Attitude control, keeping the spacecraft pointed correctly, must be maintained throughout the transit. Reaction wheels store angular momentum and allow small attitude adjustments. Thrusters provide larger corrections and dump accumulated angular momentum from the reaction wheels. The fuel required for attitude control over 12 years is a finite resource. It must be carefully rationed to last the mission duration.
Running out of attitude control fuel before arriving at the destination is mission failure. Navigation during a long transit requires precise knowledge of the spacecraft's position and velocity, not just at departure, but continuously throughout the journey. Small errors in the initial trajectory accumulate over years into significant position errors at the destination. Trajectory correction maneuvers, small thruster firings to adjust the trajectory, are performed periodically based on ranging measurements from Earth that provide accurate knowledge of distance and velocity. These corrections keep the spacecraft on course throughout the transit. Radiation effects accumulate throughout the journey. High-energy particles from galactic cosmic rays and solar energetic particle events interact with electronic components, potentially causing single-event upsets, radiation-induced bit flips in memory or logic, or gradual degradation of electronics performance. Mission designers must choose radiation-tolerant components and designs that can withstand the cumulative dose of years in space. Software must operate reliably for the full mission duration and must be updatable from Earth when problems are discovered. Flight software updates are a routine part of operating long-duration missions. Cassini received multiple software updates during its 13 years at Saturn. New features were added, bugs were fixed, and capabilities were enhanced through software uploads transmitted at the speed of light from Earth. All of these engineering constraints — power, thermal, attitude control, navigation, radiation tolerance, software — define what is possible for missions with given transit times. A 12-year Neptune mission requires components and systems that are fundamentally more robust and longer-lasting than a 7-month Mars mission. The engineering challenge scales with transit time in ways that are not linear. This engineering complexity is part of why missions to the outer solar system are expensive and take long to develop. Designing, building and testing systems that must operate reliably for over a decade in space requires extensive analysis, redundancy, testing and validation. The development cycle for outer solar system missions is typically 10 to 15 years from approval to launch, comparable to or longer than the transit time itself. A mission to Neptune that will arrive in the mid-2040s must begin serious development in the early 2030s. The components that will operate at Neptune in 2045 are being designed by engineers who are currently active in the field. The technology must be frozen early enough to allow the development and testing cycle, which means the science instruments and spacecraft systems will be designed with technology available today, not the technology available at arrival. This temporal mismatch, designing with today's technology for missions that will conduct their science decades from now, is one of the most challenging aspects of outer solar system mission planning. The instruments that Cassini carried to Saturn were designed in the 1990s. Their capabilities were defined by 1990s technology. They were good instruments, extraordinarily productive, but they would have been far more capable
if they could have incorporated the technology available by the time Cassini arrived at Saturn. Mission designers must make their best judgment about which current technologies will produce the most valuable science at the destination, given the constraints of the launch vehicle, the power system, the mass budget, and the transition time available for development. This is the full picture of what transit times mean. Not just the months or years a spacecraft spends crossing the solar system, but the years of development before launch, the operational challenges during transit, the technology freeze that defines what science is possible, the generational commitment required to see a mission through from concept to data analysis. The solar system imposes these timescales through its orbital mechanics and its physical scale. Human institutions must find ways to work within them, to maintain commitments across election cycles and budget battles and generational turnover of scientists and engineers. That challenge, maintaining the institutional continuity to execute multi-decade missions, may be as difficult as any of the engineering challenges. It requires a kind of civilizational commitment to long-term scientific exploration that transcends any individual administration or funding cycle. The transit times to the planets are the universe's terms for entry into the outer solar system. They cannot be negotiated. They can only be met with better propulsion that shortens them, with better life support that makes them survivable for humans, with better engineering that keeps robotic spacecraft alive throughout them, and with the institutional and cultural commitment to sustain missions that operate on timescales longer than any individual's career. These are the terms. They have always been these terms. Every mission that has reached the outer solar system has met them. Voyager 2 completing its 12-year journey to Neptune in 1989. Cassini completing its 7-year transit to Saturn in 2004. New Horizons completing its 9.5-year transit to Pluto in 2015. They met the terms, and in doing so, they returned humanity's first close-up knowledge of worlds that otherwise would have remained forever distant points of light. Go outside on a clear night and find Jupiter. It is usually the brightest point in the sky after Venus, a steady cream-white light that does not flicker like a star. If you have binoculars, hold them steady and look at it. You can see the 4 Galilean moons as tiny points arrayed along Jupiter's equatorial plane: Io, Europa, Ganymede, Callisto, the same moons Galileo saw in 1610 with a telescope barely better than modern binoculars. What you are looking at is approximately 600 million kilometers away at average distance. The light reaching your eyes left Jupiter approximately 33 minutes ago. It crossed the space between Jupiter and Earth in that time, 600 million kilometers in 33 minutes, and is now activating the photoreceptors in your retinas, and this is how we experience a distance so large that no other form of perception can reach it. Now ask, how long would it take to get there? Not the light, a spacecraft. A real spacecraft with real fuel and a real trajectory, launched on a day when the orbital geometry allows, following the curved path dictated by the Sun's gravity and Jupiter's position and the launch vehicle's capabilities. Approximately 18 months to 2 years on a direct trajectory, up to 5 to 6 years if the launch vehicle requires gravity assists to compensate for its lower performance. This is the nearest gas giant, the 5th planet, the one visible to the naked eye on an ordinary Tuesday night. 2 years minimum, and Jupiter is the close one. Saturn,
that faint golden point further along the ecliptic, the one with rings visible even through small telescopes, is between 3 and 7 years away. Uranus, barely visible to the naked eye and usually requiring binoculars to find at all, is 12 to 14 years away. Neptune, completely invisible without a telescope, pointed out only by star charts and patience, is 12 to 13 years away on the best available trajectory. The solar system extends from where you stand to Neptune in a span that at current spacecraft velocities takes from a few months to more than a decade to cross. The inner solar system, the part containing the 4 rocky planets in the asteroid belt, is accessible in months. The outer solar system, gas giants, ice giants, dwarf planets, the Kuiper belt, requires years to decades. And these are the numbers for unmanned spacecraft optimized for fuel efficiency on paths that follow the geometry of orbital mechanics. For human beings, the numbers are more complicated. The radiation accumulates. The bones lose density. The muscles weaken. The mind adapts to isolation in ways that require months to reverse. A 9-month transit to Mars is not 9 months of comfortable travel. It is 9 months of biological deterioration in an environment that actively opposes human physiology, managed by a crew that cannot be rescued and cannot turn back. And Mars is the easy one. The nearest planet after Venus, the one that appears as a reddish point and gets discussed in terms of human missions within this century. Let us be honest about what these numbers mean at the full scale of the solar system. The transit times are not inconveniences to be solved by better technology, though better technology would help significantly. They are the solar system's actual dimensions, expressed in the one unit that always matters: time. Human time, career time, life time. The Cassini spacecraft took 7 years to reach Saturn. The team members who built its instruments spent 7 years of their professional lives waiting for the spacecraft to arrive before the real science could begin. The scientists who are today's graduate students, preparing to work on a Uranus orbiter that might launch in the 2030s, will be approaching retirement when that spacecraft arrives at Uranus in the 2040s. The science they will produce will define their careers. But they will have spent decades waiting for the transit. The Voyager spacecraft, launched in 1977, took 12 years to reach Neptune. They have now been travelling for 47 years. They are in interstellar space, past the heliopause, beyond the heliosphere, in the true void between stars. They travel at 17 kilometers per second. At this speed, they would reach the nearest star, Proxima Centauri, 4.24 light-years away, in approximately 73,000 years. 73,000 years to the nearest star at 17 kilometers per second. The solar system, with its transit times of months to decades, sits at the near end of a scale that extends vastly further. The interstellar distances that begin where the heliosphere ends require either timescales measured in tens of thousands of years at current velocities, or technologies, fusion propulsion, light sails, concepts not yet built, that don't yet exist at practical scale. The transit times to the planets that we have been discussing, the months to Mars, the years to Saturn, the decades to Neptune, are the achievable portion of an exploration challenge that extends indefinitely outward. And yet, those transit times, long as they are, have been met. Every planet has been visited by spacecraft launched by human civilization in the last 60 years. Every gas giant has been photographed in close-up. Saturn's rings have been mapped in extraordinary detail. Titan has been landed on. Enceladus's ocean has been sampled indirectly by flying through its plumes.
Pluto's mountains of water ice and plains of nitrogen have been photographed. The surfaces of Mars have been driven by rovers for years. All of this happened. All of it required meeting the transit times, committing the years and the engineering and the institutional continuity and the human attention necessary to send something across those distances and wait for it to arrive. The transit times demanded commitment. The commitment was made. The knowledge followed. This is what the solar system has required of us. Not genius, though genius was involved. Not unlimited resources, though significant resources were committed. What the solar system required was time. Years and decades of sustained effort, maintained across the transit times, maintained through the years of quiet cruise when nothing spectacular happened and the spacecraft were just traveling. Maintained through the budget battles and political changes and institutional turnover that constitute the normal background noise of large scientific programs. Every planet in the solar system has been visited because someone, many someones, sustained that commitment through the transit times. Through 18 months to Jupiter, through 7 years to Saturn, through 12 years to Neptune. What would you be willing to wait for? The question is not rhetorical.
It is the actual question that transit times pose to any civilization contemplating solar system exploration. Not, can we build the spacecraft? That is an engineering question. Not, can we afford it? That is a budget question. Can we sustain the commitment through the years of transit? Can we maintain the institutional focus and the funding and the trained personnel and the scientific priority across the years between launch and arrival? The history of solar system exploration shows that this is possible. It has been done. The Cassini team sustained its commitment for 20 years, 7 years of development, 7 years of transit, and then 13 years of orbital science at Saturn. The team that built the Galileo spacecraft in the 1980s and waited through 6 years of transit to see it arrive at Jupiter in 1995 showed that years-long commitments could be sustained through the full arc of a mission. The solar system is not closed to human knowledge.
It is accessible at the price the orbital mechanics demand. The price is time, always specific amounts of time determined by the distances and the velocities and the gravity. Mercury, 6 to 7 years. Venus, 3.5 to 5 months. Mars, 6 to 9 months. Jupiter, 18 months to 6 years. Saturn, 3 to 7 years. Uranus, 12 to 14 years. Neptune, 12 to 13 years. These are the terms. These are the actual transit times to every planet. Not the diagram in the textbook, not the simplified animation, the actual times that actual spacecraft traveling at actual achievable velocities on actual feasible trajectories require to cross the actual distances of the actual solar system we actually inhabit. They are longer than most people imagine, much longer for some destinations than intuition would suggest. The counterintuitive reversal, Mercury taking longer than Mars, despite being the closest planet to the Sun, reveals how deeply orbital mechanics differs from the simple geometry of distances. But they are finite. Every one of them is finite. The journey to the farthest planet, Neptune, at 12 to 13 years, is longer than most people's graduate school and postdoctoral training combined. It is a significant fraction of a career. But it is not forever. It is not impossible. It has been done, once, by a spacecraft launched in 1977, which arrived at Neptune in 1989 after 12 years of transit, and which returned data that transformed our understanding of Neptune and its moon, Triton. The transit times to the planets are the solar system's terms for the knowledge it holds. Those terms have been met, planet by planet, mission by mission, over 60 years of human spaceflight. Each time they were met, something previously invisible became known. Io's volcanoes, Europa's ocean, Saturn's rings in detail, Titan's methane lakes, Enceladus's plumes, Pluto's heart-shaped nitrogen plains. Each piece of knowledge required meeting the transit time, committing the years, sustaining the effort, waiting through the quiet months of cruise, and being present when the destination finally grew from a point of light into a world. The light from Jupiter reaching your eyes tonight left that planet 33 minutes ago. To send something there and have it arrive, to meet the transit time on the journey that those photons made instantaneously in the opposite direction, would take 18 months to 2 years. The solar system is right there, at the price of years. The price has been paid before. It can be paid again.